So, the final straw in the hat is spectral factorization. It is nothing new, we are not going to learn anything new per se, but what we are definitely going to learn is the conditions under which I can build a linear model for a given random process. So, now we are asking the most fundamental question. We have discussed already AR models, MA models, ARMA models, we have talked about spectral densities and so on. Particularly we have talked, I am focusing on AR, MA and ARMA models, but we have evaded the question under for what class of processes I can construct such time series models. And of course, I have briefly talked about it, but now is the time to go a bit deeper. So, if you recall, the question now that we are asking is when can I build a linear model, and if you recall the linear model, this is essentially your linear model, and you should be able to express Vk as a linear combination of past, present and future shock waves, subject to the condition that the coefficients are absolutely convergent and Ek is a white noise. Now, we know already from spectral representations that the spectral density of such a process is what we have seen already, sigma square E by 2 pi times mod h of e to the minus j omega square. Okay. So, if you look at it, the problem of fitting a time series model can be recast as a problem of factorizing the spectral density into 3 factors. What are those 3 factors? Essentially actually 2 factors, we do not talk of 3 factors, but let us talk say 3 right now. Sigma square E, okay, 2 pi we will ignore, fine, that is a matter of choice of omega. Sigma square E, h of e to the minus j omega and h star its conjugate, correct. Normally we do not include sigma square E as a factor, we say that that is a multiplicative constant. We refer to h of e to the minus j omega as a spectral factor. Now, obviously the issue here is that this factorization is not unique. There is some thing that we know, one of the factors is a conjugate of the other, which is good, which actually reduces this ambiguity about non-uniqueness, but otherwise we have already discussed this, right. We have said, look, if h and sigma square E, if a set is a solution, then h by alpha and alpha square sigma square E is also a solution. In other words, I can multiply the spectral factor h of e to the minus j omega by some alpha in this factorization and divide sigma square E by alpha square. Why alpha square? So, all I am saying is if I adjust the spectral factor h by a factor of alpha, then I have to adjust h star also, remember, and that is why I need to adjust sigma square E by alpha square. So, there is this non-uniqueness and we fixed that non-uniqueness by requiring that. How did we fix this non-uniqueness? First coefficient equals 1, which means now I am not permitted to multiply h of e to the minus j omega by alpha. I have already fixed, right, and that is how we fix the non-uniqueness. But now let us ask, when is this spectral factorization possible? When is it possible to find a spectral factor? What is so special about the spectral factor? How is the spectral factor defined, h of e to the minus j omega? Yeah, it is what? It is the Fourier transform of impulse response sequence, correct. By the way, here we are not talking of periodic processes, remember. Why are we not talking of periodic processes? Because we know that the ACVF should be absolutely convergent and so on for this kind of model to hold. So, we cannot bring the periodic processes into this gamut, we are only talking of aperiodic processes. That is why I said we are specifically talking of AR, MA, ARMA models and so on. So, h of e to the minus j omega agreed is a factor, but it has something special about it. It is a Fourier transform of impulse response sequence, correct. So, that is an additional requirement. I cannot obtain any factor. I should obtain a factor such that it is a Fourier transform of some sequence, and that sequence should be absolutely convergent. So, there are so many things that are required of this factorization. If you are not following what I am saying, it is easier to think of it in this way. Fitting a time series model amounts to factorizing the spectral density behind the scenes. You may not be factorizing the spectral density, we do not. When you fit an AR, MA or ARMA model, we never talked about spectral density factorization at all, spectral factorization. We always talked about fitting the models. But what we are saying right now is fitting a time series model amounts to factorizing the spectral density. This was a profound finding in the theory of random processes. Only when they discovered these connections, people were able to come up with answers as to when you can fit a time series model. Okay, that is why this is called a spectral factorization result. So, the spectral factorization is the inverse problem, we have talked about it. Given a continuous symmetric non-negative spectral density gamma, find a spectral factor, and we already discussed what a spectral factor is. So, why is spectral factorization important? I have already talked about it. Now, the question that we want to answer is under what conditions is it possible to obtain the factorization, and when is it unique, right? And are there any restrictions on gamma? Can I factorize any spectral density? First, I should be guaranteed that gamma of omega is a spectral density, and we have already talked about the qualifying characteristics of a spectral density, the symmetricity, evenness and so on, periodicity. So, what we will do is by and large we will avoid the proofs and so on, we will go straight away to the answers to these questions. The proofs are fairly involved. In fact, by going through the proof, you can actually show that a random stationary process whose ACVF is absolutely convergent or spectral, for which then a spectral density exists, it is possible to express it as a linear combination of white noise. I will upload that proof later on, it is slightly involved, but I will upload that proof. I will try to make it as simple as possible, but it is a very nice elegant proof to show that indeed for a random process whose ACVF is absolutely convergent, which means the spectral density exists, it is indeed possible to show to express that random process as a linear combination of white noise. The white noise process takes birth from that proof, in fact. That is how the concept of white noise itself you can think was born. So, we will avoid all these derivations. I will also avoid the major, I will only point the major things. One of the things that you will come across in general when you read these proofs is the generalization of gamma of omega to gamma of z. For those of you who are familiar with linear systems theory, there is a Fourier transform and then there is a Z transform. The spectral density is a Fourier transform of ACVF, and here we are talking of gamma of z, which is a Z transform of the ACVF. It is nothing but your autocovariance generating function. We have seen this before, nothing special. The proofs will involve gamma of z, and that is why I talked about it. So, we have talked about this spectral uniqueness of the solution, we require that h of 0 is 1. The other point that you could have now thought of or imagined already is that in that factorization I can always adjust the phase of h of e to the minus j omega. What this means is I can always multiply h of e to the minus j omega with some e to the minus j phi. Why is that? Because the complex conjugate will cancel that out, which means that I can always fit a time series model only up to a phase ambiguity. There is always a phase ambiguity in that. In other words, if the shock wave, there was a delay between the shock wave, the fictitious shock wave white noise and the process that you are looking at, you will not be able to identify that delay. That is a classic problem with time series models. You will not be able to identify because that delay will manifest as phase, and therefore, it is not possible to resolve the phase in any time series model. I am talking of univariate time series models, beware. When I am given a single series, I can only figure out the relation between this fictitious shock wave and the given signal, but not the phase. The rest of it can be figured out. That is not the case in regular system identification or when I am given the input. When I am given the input, the phase is fixed, because then I have a fixed input. Here the input is not fixed in some sense, only its statistical properties are fixed. So, that is something to remember. And the other point that we have also realized earlier is, if h of e to the minus j omega is a solution, h star of e to the minus j omega is also a solution. We have talked about this invertibility, if you recall. We have said, remember the example that we went through, MA1, we had C1 and 1 over C1 as a solution, and then we picked the factor that is invertible. So, just to give you an example, suppose I have this ARMA process. This ARMA process you see is neither invertible. Is this invertible? It is not invertible, nor is it stationary, or in other words, nor is it causal. Amazingly, you can actually, when you write the spectral density here, see the existence of spectral density is not conditioned on the invertibility or causality there. I can always find, remember, a stationary representation, but in a non-causal sense. So, here is a spectral density, and then I can always rewrite the spectral density or refactor in such a way that I have a new spectral factor. All is just algebraic jugglery there. We are rewriting now gamma of omega in such a way that I have a new kind of spectral factor, and as a result this is one of this is the alternative representation. Okay. So, I have 1 plus 3 q inverse over 1 minus 2 q inverse as the model, and I can actually find 1 plus 1 over 3 q inverse and 1 minus half q inverse as a model. So, you can actually find a factor that is both invertible and causal. Just a simple example, you can go through this example, but what is the difference that you see? That sigma square E is different now, right? That is the difference now. Now that we have adjusted for causality and invertibility, the variance of the driving force has changed. So, let me now summarize some of the main conditions for existence of factorization, and then we will close the discussion on spectral factorization. So, first of all, on non-causal, right, two-sided, first we are talking of non-causal, because our linear random process model, if you recall, allows both future and past shock waves to affect the signal. So, first we answer that question, when is it such a representation possible? It turns out that it is possible for all processes that have continuous spectral densities. There is no major restriction per se on that. But what is more important is causal representation. So, we are starting from non-causal, and then we want causal. What we mean by causal is we only want past and present shock waves to affect the signal. We do not want models that rely on future shock waves to explain the present. Ultimately, what is modeling all about? It is all about basically trying to explain the given signal in terms of some shock waves. So, what we are saying is, if it is only a matter of explaining the signal in terms of past, present and future, then there is no major issue. As long as the process has a continuous spectral density, you should be okay. But if I want a model that is useful in practice, a non-causal model is not useful in practice, because I need future shock waves to make a forecast. What I want is a one-sided model, right? I want a model that has this form, n running from 0 to infinity. When is this kind of a model possible? What restrictions one has to place on the spectral density? And the restriction is that this particular condition known as the Paley-Wiener condition should be satisfied by the spectral density. If I am only worried about this kind of a representation here, two sided, then there is no restriction. Any process that has continuous spectral density, you should be able to do it, right. But this result says if I want this kind of a model which is useful in practice, then additionally the spectral density has to satisfy this condition. Okay. This is called the it should be so the integral logarithm should be greater than minus infinity, between minus pi and pi. What else is a requirement? Is this enough or do we need more conditions? Are we okay with just this kind of models or we need any other? Remember the condition that h of n should be absolutely convergent holds, that is guaranteed. What else do we need? What kind of a model is this? Is it a moving average or an autoregressive model? Moving average, right. But I should also be guaranteed that an autoregressive model be constructible. I should be able to construct an autoregressive model. What this condition states is you will be able to construct a moving average model of infinite order provided the spectral density satisfies this. Do not worry about whether I know in practice, I do not know. In practice you or I will never be able to verify whether for a given process this condition is satisfied or not, and in general, but maybe for some it will be obvious. But most of the times you will never know whether this Paley-Wiener condition is satisfied. You only hope and pray that it is satisfied and proceed. What else is required? So, if I want to be able to fit an autoregressive model, what else should be guaranteed? Invertibility of this model should be guaranteed. Okay. If I have to be able to build a stationary AR model, then invertibility should be guaranteed, in which case the logarithm of the spectral density should be analytic in that annulus. Okay. It is just a condition that you just have to know that there exists a condition further on the spectral density for you to be able to obtain an invertible model, which means what we mean by this is for you to be able to construct an autoregressive model. So, there are three. One is most general when you had minus infinity to infinity, where the spectral density, any process with continuous spectral density, you should be able to build such a model. And then secondly we said no, I want useful models. Now tell me whether I can build this model for any process. The answer is no. Any stationary process that has continuous spectral density and which satisfies the Wiener-Paley condition should be able to do it. And then thirdly, we want to be able to construct an autoregressive model, and that means that I should be able to construct an invertible model, and invertibility is guaranteed when the logarithm of the spectral density log gamma of z, now we are not talking of log gamma of omega, that should be analytic in this annulus. Analytic essentially means that this function gamma of z should not take on indeterminate values. That is what analytic means. It comes from functional analysis. So, this condition guarantees that I can build autoregressive models. So, these are the three main results, and so if you put together, if you have a discrete time stationary process whose spectral density, of course, by spectral density itself we mean symmetricity, integrable. Why integrable? Because variance should be finite, non-negative, and of course periodicity is not what I mentioned, it should be also included. Further, now we have included a log analytic requirement. If there exists a stationary process whose spectral density satisfies all these conditions, then you can actually perform spectral factorization, means you can fit a time series model. Okay. So, first we learnt what are time series models, what are the features of time series models. Now we are answering the question, when is it possible to fit a time series model? Can I fit this for any process? Okay. The last question that we want to ask is, when the spectral density has a rational form, until now we have not said anything about the form of spectral density. We only said if the spectral density satisfies all those conditions, I will be able to fit a model of this form, right. But now if we specifically say I want to fit an MA model or an AR model of a particular order, then that means I am parameterizing H and I am parameterizing ACF and I am also parameterizing spectral density. We have already seen for ARMA models the spectral density has this form, correct. In this case only I can fit a time series model that will exactly describe the process. Now we want to ask the question, what about a general gamma of omega that satisfies these conditions? It satisfies this, but it does not have this form. And I still want to fit a time series model. I am still going to go ahead, you can't hold me. I am going to fit a time series model because that is what is needed for forecasting. Then what? Am I making a big blunder by fitting a time series model to a process whose spectral density does not meet this, does not have this rational form? The answer is this, right. I mean, I am going to skip that example, we have already talked about it yesterday. The answer is that if you fit, this is in the form of the theorem, which says that if you fit an autoregressive model of a sufficiently high order, then as long as the spectral density meets, of course, it is already understood that your spectral density meets all the requirements, regardless of whether your spectral density has that, what form it has, you will be able to approximate the spectral density with an arbitrary degree of accuracy. So, to summarize, if you do not like any of this theory and so on, to summarize, for a process whose spectral density exists and satisfies some important conditions, you can fit a suitable time series model that will explain or that will be able to forecast or predict the given process with a fair degree of accuracy. It does not talk of forecasting, but at least it says it talks about spectral density, it is very careful, it does not talk of forecast. But the good news is you can fit a time series model. How well you will be able to fit depends on now the length of the data that you have, the kind of estimation algorithm that you are going to use, how you choose your order, what is the methodology that you follow and so on. That determines the kind of model that you build. So, until now we have talked a lot about theory and in bits and pieces of estimation, like we have talked about Euler-Walker's method, sometimes method of moments and so on, and occasionally we have talked about variability of parameter estimates when we talked about covariance and so on, but largely we have talked about theory, what are the possible models, what is meant by spectral density, how do you describe a random process in both time and frequency domains, when is it possible to build time series models and so on. So, you can say now enough is enough, you have learnt a lot about theory, time to turn to practice. Of course, in R I have shown you how to do it. By the way, the ARMA spec, as I said, from the TSA package will allow you to construct the theoretical spectral density for a given ARMA process. You should just try it out, it is very simple to use like your ARMA ACF. So, now we should turn to estimation and ask, tell me how to estimate a good model. What are the things that I have to worry about in estimation, right? Those are the things that we are going to talk about. I will just spend about 3 or 4 minutes and then of course, we will carry on with the next week. So, this kind of concludes the theoretical discussion on the theory, and now we step into the theoretical discussion on practice. So, there is still a theory of practice. You can't say simply because it is practice I will do as I please, it is not possible. You have to guarantee that you will obtain good estimates of model parameters, you will obtain so called consistent estimates, efficient estimates, you have to guarantee unbiasedness, so many things you have to guarantee when you use an estimation algorithm. Otherwise, it is your own personal choice that you can live with and be happy, but you can't convince the scientific community at large. That is the main point. Okay. So, there are a bunch of references. I will not talk of coherence right now, we will talk about it a bit later, but that kind of concludes the discussion that I wanted to have on univariate time series analysis. Just want to briefly talk about estimation and then we will continue with next week. So, we have just now said and talked about when can we fit a model and so on, and now we said we need to focus on how to fit a model. We have talked about types of models, when is it possible, theoretical conditions, and now we are talking about the how, and that is essentially your estimation. And when you step into the world of estimation, you realize that estimation is perhaps the oldest exercise that you can ever have. You could have ever come across, because maybe from the time humans have started to think and analyze situations around, inferencing or estimation is a natural thing that would have occurred, right. I mean, when I am looking around, I am trying to gauge how far I have to go, what is the width of some room, or what is the width of a river that I have to cross. All of this is estimation, except that now today we have a formal way of estimating, but otherwise we keep estimating every moment. You must be estimating how many minutes more to go before this class ends. So many things that you estimate. So, one runs into different estimation problems, and one of the classic problems that you run into is parameter estimation. And when we mean parameters here, not only model parameters, but also parameters of PDFs. Okay, do not just think of model parameters all the time. The parameters of the PDF, for example, if I look at a Gaussian PDF, then I have mu, I have sigma and all of those, or I can think of estimating signal properties. What do we mean by signal properties? Again, mean, variance, spectral density, all of this is the estimation problem of signal properties. Then we have a state estimation problem or signal I give you measurement and I want you to estimate the underlying signal. For example, I give you sinusoid embedded in noise. I want you to recover the sine for me. That is a classic signal estimation problem, which was extended later to a state estimation problem by Kalman. I do not know how many of you know, Kalman recently passed away in July this year. So, Kalman essentially extended Wiener's ideas of signal estimation to state estimation, right. Wiener was solving more or less a steady state problem where the signal does not change with time, and Kalman said no, the signal can change with time, and let me actually put in a model for the signal, evolution model for the signal. Given the model for the evolution of the signal, how do I estimate? That is essentially your state estimation problem. So, any time series analysis or any analysis for that matter has the estimation at its heart. You cannot evade it at all. Therefore, you should be extremely well versed with estimation, and that is why we take time off now to spend to discuss on estimation, and the device that performs estimation for us is called the estimator. Okay, sounds like Terminator or something, but it is called the estimator. It is a virtual device. In fact, the sensors that we use are also estimators, all right. And what does estimation theory offer us? Three things, and it is very important to understand. First, the estimation theory offers us methods for estimation. In fact, most importantly, I would say means for assessing the goodness of the estimates, but let me order it in this way. It gives me methods for estimating. How do I estimate the mean? We have talked about mean, variance, spectral densities, covariance, autocovariance and so on, model parameters. What are the different methods available? Secondly, once I have estimated, estimation theory shows us how to assess the goodness of the estimate, right. And the classic, one of the examples that I always give is, suppose I have a piece of land and I want to build a house, right. Someday you will do that, maybe you are already doing, I do not know, but someday you will do it, and that time you would approach a few builders who will give you estimates, cost estimates of constructing the house. They are all giving you estimates, but then at the back of your mind you are assessing the goodness of such an estimate, how reliable is the estimate and so on, correct. And there are different criteria that you have in mind, but the most important, one of the most important criteria is, if I were to ask the builder again, if I ask today and I ask tomorrow, right, or I call 2 hours later, where the market prices would not have changed much, the builder should not give me a completely different price, right. Now at this point in time, the builder may say it will cost you about 30 lakhs to build a house, and you call 1 hour later and says, no sir, it costs you about 45 lakhs. That is too much variability, which is what we call as variability. You want to keep the variability low. He may say, okay, 30.5, which you are okay with it. He must not have factored something, or something must have drastically changed over the 2-3 hours time. But you can't expect, at the scale of the variability of the process, given the scale of the variability of the process, your estimate should not change too much. That is one of the most important criteria. Then there is another criteria called consistency, where I give infinite observations, I give a complete realization. Will you be able to estimate the parameters accurately, right. So, there are some properties, and finally, in making confidence statements, that is, after having estimated and after knowing how good the estimate is, we want to be able to say something about the truth. That is the most important thing, right. Why are we actually estimating? Because we want to say something about the truth. So, when the builder gives you an estimate, what would you ask? You will say, give me a rough interval. Will you be satisfied with the point estimate? What the first answer that comes out is a point estimate. Then the next answer that you will seek is an interval estimate. So, ultimately we have to go to the interval. We may begin with point estimate, but we have to go to the interval. What is this interval? This interval contains hopefully the truth. The builder may say, okay, it may cost you somewhere between 30 plus or minus 5, right. Do you think finally the actual cost will be in that interval? Is it possible always with 100% confidence? It is likely that the actual cost may be outside this interval, but there is a degree of confidence that the builder would attach to that interval. Say, sir, 90% your cost will be, actual cost will be between 30 plus or minus 5. That means there is a 10% chance that the reality is outside this, right. That degree of confidence gives you an assurance that you can go with this builder. So, that is the basic idea. Okay. So, we are going to learn formally how to, we will begin with assessing, knowing how to assess the goodness of an estimate, and then learn how to estimate itself. Why do we choose that order? Because when I discuss a method for estimation, I need to know how good the method is, and for that I need to know the metrics of goodness. So, that is why we will begin with a very simple estimation problem next week, and then quickly move on to assessing the goodness of the estimates, followed by methods of estimation. Okay. So, we will meet next week. Thank you.